You're listening to EE Times On Air, and this is EE Times Current. For Eric Singer, I'm Taylor Marvin. Welcome to Brains and Machines, a deep dive into neuromorphic engineering and biologically inspired technology. In this episode, Dr. Amirreza Yousefzadeh talks about his work building AI systems on a chip. Your hosts are Dr. Sunny Bains of University College London and Dr. Giulia D'Angelo of Fortiss in Munich.
Welcome to Brains and Machines. I am Giulia D'Angelo.
And I'm Sunny Bains.
In today's episode, Sunny discusses hybrid neuromorphic chips with Amirreza Yousefzadeh. After the interview, we'll be talking to Ral Fan Etienne-Cummings from Johns Hopkins University about the issues raised.
Thanks, Giulia. Amir has been around a lot of labs over the years, working in Spain, where he got his PhD, France, Belgium, the UK, Singapore, and most recently in the Netherlands, where he's worked at Grey Matter Labs, imec, and as you'll hear later, at the University of Twente. He has a broad background in electronics, starting with digital and then moving into neuromorphic. And he's spent time both in industry and in research. This sets him up neatly to work on hybrid AI systems on a chip. There are links to his work and some of the specific papers we'll be discussing on our website. You can check them out at brainsmachines.net. Amirreza Yousefzadeh, welcome to Brains and Machines.
Thank you, Sunny. It's an honor.
Let's start by talking about your technical background. What did you study and how did you get interested in neuromorphic engineering?
I did my bachelor and master in electronics, more specific digital electronics. In 2014, I was looking for doing a PhD, and at that moment, Europe was running a big project called Human Brain Project. And then I got a scholarship from the Spanish government to join a Spanish Research Council, a branch of it in Sevilla, with a well-known professor at that moment, Bernabé Linares Blanco. He was part of Human Brain Project, especially the Spinnaker project that was also led by the University of Manchester. And then it was actually, for me, the beginning of my journey, but it was also almost the beginning of this Human Brain Project, which had great results. It just finished. It was a 10 years project. And during that project, several neuromorphic chips has been introduced, but also outside of Europe, in US, for example, the mainstream neuromorphic processor was started by TrueNorth. It's another chip from IBM. And it was also introduced, I think, a year after I started my PhD, like 2015. And then Intel introduced its chip in Loihi. It was the first one in 2018. So it was basically the hype of neuromorphic being deployed and a lot of hope for commercialization at that moment. So I started 2014 and then I finished my PhD in 2018. But there was also, in parallel, deep learning research that was going on. We have now a lot of scientists being worried about the result of AI. 2014 was mainly the maturization phase. And during my PhD, we tried to use a lot of results that was developed in the deep learning world for the neuromorphic. So my PhD was mainly about doing on-device learning on neuromorphic chip, which is still an open research topic.
Would it be fair to say that you were, right from the beginning, interested more in how to get these brain-like or neuromorphic ideas into products than you were into, for instance, the neuroscience, understanding the brain, these aspects?
When I started my PhD in our institute, the group was working on event-based vision sensors and also some neuromorphic processing chips. At that moment, actually the first 6 months of my PhD, I was just amazed about the potential of this technology, and this can be so cool. But then, of course, every PhD after maybe a second year and a half, you go to this depression phase that this technology doesn't work well. And at the end of my PhD, I was also collaborating with a company called BrainChip in US. We were doing a lot of cool research, but they were always coming back at how we can actually make a product out of it. And these questions always triggered us to think about actual potential use cases in the market. It also triggered me to look into what are the competitors in the market, especially in non-neuromorphic domain, what others are doing. And I think it had a good inspiration on me that what we need to make should have market value.
I understand you used to work at Gray Matter. Would you like to say something about the work you did there and how you got to imec, which is where you are now?
Yeah, so when I finished my PhD, I joined imec as a postdoc. A few months after I started my postdoc, I was thinking maybe postdoc is not the right thing for me. And then I was contacted by my PhD supervisor that he actually founded a company in Netherlands together with some other professors from Zurich and from Paris to build neuromorphic processors. And they offered me a good position to be the hardware architect there. So I terminated my postdoc after 6 months, and then I joined the Gray Matter lab. And their initial idea was to build a processor which is using neural network to do the compute. So exactly the other way around that most other companies was doing. Most of the companies were using the compute for neural network, yes. So this is thinking out of the box to build neural network type circuits that we use to do normal compute. And yeah, the idea was actually started a year before I joined by another team in Paris, led by Dr. Riyad Ben Osman. He got funding from DARPA. And then when we joined, it was in the form of a company. So the seed was gone. They got some funding from the venture capitalists, and they wanted to fabricate a chip. Again, another phase of this commercialization. When we think about company, when we think about people that expect you to have a product in a couple of years, we needed to change from the initial idea to make something a bit less risky, I would say, to be able to compete. Especially we had our product managers were always telling that I talked with this customer, with that customer, they want to run ResNet 50. And then they ask how much does it cost to run ResNet 50 on your chip. Yeah. So everybody at that moment were talking about running neural network. Nobody really cared about doing compute on a chip because their processors for the compute are quite mature. So the customers were contacting us, asking us how efficient it is to run neural network on the chip. So then we changed the idea a little bit. We started doing a hybrid processor that does both compute and neural network. So for the compute, we were using a structure which is called data flow, which is very similar to neuromorphic architecture. And this way, we tried to merge these two concepts together. I was 2 years at Gray Matter Lab, and then some incident happened. One of the incidents was that the company was going toward more building products and commercialization. And then they decided to reduce a bit of the research budget. So our team, which were doing research, became a bit smaller. And some type of collaborations they had with some partners, which I personally didn't like. So then I decided to go back to imec. My inherent type of work didn't change. I was again hired as a neuromorphic hardware architect, but imec is a research technology organization, not for profit. So it allows me and my other teammates to have a lot of freedom to do research. And I tried to basically work on the research questions that I had during my work back in Gray Matter Lab. And I think the research we are doing, of course, is also useful for companies and startups. So it's a mutual benefit.
So it's nice to be free of those constraints that you have within a commercial company.
It's good to have a bit more freedom, but being completely free of the market, this is not something I like because I want to eventually make useful things. But imec is the exact trade-off. It's a company that is supposed to commercialize technologies coming from universities. So I think it's the right place.
Now, I know that the thrust of your recent work has been a new chip called Sena. Can you talk first about what you wanted this chip to do?
Yes, Sena was started, I think, in 2020 because we had some European funded projects that asked us to build neuromorphic chip which are in one side scalable, so it can address the issue that we always have with neuromorphic chip, that the neural network model should be tiny and small. And on the other hand, it's supposed to serve a wide range of applications. For example, the applications we had at that moment was doing denoising of medical images. This is maybe not the right application that a neuromorphic engineer think, but it was just an example to say that if we can do such a thing, we can do many other stuff that maybe most neuromorphic chips are not able to do it. We also had a parallel track to do a very tiny neuromorphic chip that served for in-sensor processing. We called it microbrain. So Seneca was supposed to be a complementary track. So we diversify our portfolio when we talk with customers and other partners. So Seneca initially designed to be more flexible chip, scalable, allows us to do stuff that we cannot do with other small scale neuromorphic.
Okay, so I know that for this chip, you've spent a lot of time thinking about optimizing different kinds of technology and thinking about what's really needed and where on the chip. Can you talk about some of these design decisions you took and why you took them?
Yes. From the beginning, it was clear that Seneca is supposed to be using conventional digital technology. So in imec, because it's a micro-nanoelectronic institute, has a huge freedom to choose between a lot of microelectronic technologies. A lot of them, they are not even available outside of imec. So we are in a good position. But for Seneca specifically, for the initial phase to come up to something that is working, we were trying to limit ourselves to what is available outside imec for any commercial technologies, yes. This actually imposed a lot of constraints. We roll out something like analog compute. We roll out something, let's say, exotic memory technologies, yes. And we try to see with this limited freedom, what can we do? What is the optimized version of doing it? The challenge that this set of constraints brings is that if we want to do a completely brain-inspired compute platform, it will not be efficient. So we needed to get inspiration both from neuromorphic concept and brain-inspired compute, and also advanced compute technologies, like the advanced processors that we have in the computers, yes. So one thing we decided to do is trying to see how different memory technologies that are available in the market can fit in the compute platform, because memory is the part that consumes biggest area and biggest amount of power consumption in any neuromorphic chip that you see. So we saw that there is a various amount of memory technologies, register file, SRAM, DRAM, HBM memories, MRAM memories, which are recently commercialized and non-volatile. So one of the things that we decided is that the architecture should be able to use a hybrid memory technology. So various memory technologies in different places where they bring their own advantage. And this way we showed that we can have both area efficiency and power efficiency in the same time. There were some of the concepts that we borrowed from the conventional world, which is proven to be efficient for digital. Some concepts we borrowed from the brain-inspired compute, which are not yet proven to be efficient. They are still research questions, but we believe that it's a good amount of risk that we bring those concepts. For example, one of those concepts is that we use this tiling of a lot of small processing cores with each other in a chip, which you don't see it in a commercial processors. Like the processor that we have in the laptop, they don't use this kind of tilings with a knock option yet. Yes, they are still thinking about it, but it's not yet proven to be very efficient, but it allows scalability. It brings a lot of freedom. So we thought that this is a good idea to bring from the neuromorphic domain. Another thing is the concept of near or in-memory processing. And this is a concept that is both validated by bio-inspired processing and also conventional processing. So it's a common point. There is one technology that we used, which is RISC-V processor. It's a technology which is actually borrowed from the conventional world, but it's not very common. It is an emerging kind of processor architecture. We used it because we find it brings a lot of advantage to our processors while don't take too much area and power.
So my understanding is that essentially what you've tried to do is really think hard about all of the different things that a user might want to have on a single chip. And that's why you've gone for some very conventional looking technologies, as well as some very neuromorphic looking sections of the chip, so that just everything that you might want is there for your application rather than having to go from one chip to another. Have I got that right?
Yes, exactly. We try to look into the application end to end and see that if we want to have an application running in our chip, where should be optimized? Because many designers may look, including me during my PhD, we were looking at a small part of applications, trying to optimize it. But then for a real life scenario, we see that part that we optimize 20%, but there is this huge place for improvement for other parts as well. Here in Seneca, we try to design it in a way that we can deploy an application end to end. What we had always as a vision is that this processor is an event-driven processor, which is inspired from neuromorphic technologies. But then the definition of event, we make it a bit flexible to cover a wide range of applications. We try to do more than just neuron integration and firing with this kind of process that we apply on the event. So we considered our processing pipeline as 3 phases: event pre-processing, event processing, and event post-processing. And this pre-processing, post-processing, there are many times this non-neural network type of processing that you need to have in place. If you don't have it integrated inside your neuromorphic core and then put it somewhere outside, it adds a lot of overheads. So we try to remove that overhead of pre and post processing.
And my recollection from reading your papers is that you had 2 different kinds of controller on your chip. Can you talk about that?
Yes. In a neuromorphic core, when we try to deal with this constraint of digital technologies, one of the techniques we are using is time multiplexing of neurons. So instead of implementing 1,000 physical neurons like you need to have in a core, we implement a smaller set of physical neurons, like 8 or 16 physical neurons. And then we time multiplex it to emulate these 1,000 physical neurons. This is a concept that is employed by most digital neuromorphic chips that you see. And then when we introduce this kind of mechanism, we need a controller in place to take care of the synchrony of all these operations that need to be done. For this, we had 2 options: either to use a very general controller that allows a huge freedom for us. So we can do a lot of other stuff. For example, we are not obliged to use a specific neural model or a specific ratio of time multiplexing. Or we go all the way to make it a very optimized controller that does very specific things, highly efficient. Yes. You can guess each of them has a kind of disadvantage. So eventually, maybe a bit unconventional in the neuromorphic domain, that we actually put 2 controllers in place. We put the both more general and flexible controller and very efficient one. And the overhead of doing this is, of course, extra 10% area that we pay for this RISC-V controller that we have. But it actually have a huge power advantage in a way that whenever we want to use a smaller controller, we turn off the big one, we don't use it, and then we go with highly power efficient process. And then whenever we cannot do something with this small controller, we do it with the big one. But this is a concept employed in conventional processors where they call it big little architectures. We try to adapt it to our own process.
Now, you were talking about the time multiplexing of these neurons, and I'm guessing that's what you're using this memory in compute for partly, that you're storing the weights locally?
Yeah, first of all, time multiplexing is still a controversial topic in digital neuromorphic architecture. So Many designers, they do time multiplexing, but they're not happy of what they do. It's like a bad constraint, yes. But time multiplexing is used almost in all the neuromorphic processors because this is something, it's basically an advantage that digital compute provides to you. So why not use it? And when we use time multiplexing, we use a set of physical neurons and then we replicate it for a huge number of neurons, yes. Therefore, we need to load and store back the state of the neurons to these physical neurons all the time. Yes. So that's a problem that neuromorph have with time multiplexing because we need to a bit separate these two concepts of compute and memory to be able to do time multiplex. That's a disadvantage it brings next to all this controlling overhead.
Okay, so what's your plan for this chip? What will be the next steps?
So initially, when we tried to design this chip, because it was funded by several EU-funded projects, the idea was to build a platform so we can experiment a lot of stuff and learn from it. And then we allow also our students to use it and then experiment and learn. A year ago, when we finished this platform, it was in this stage that we tried to learn how to further optimize things in a concept of a tiled event-driven processor. So many of the concepts or innovations that we applied on a platform like Seneca is actually a standalone, can be usable in other similar neuromorphic processors. That was one of the goals. But then over time, when we show advantage and then we optimize the processing further and further, we are now thinking about commercialization. We are at this moment trying to prove that architecture like Seneca can compete with some more conventional architectures like what we see in the market, let's say these AI accelerators from NVIDIA or from Intel, yes. It is very important for our program to show very soon that we are competitive enough against the conventional architectures. We try to, step by step, bring some topics from neuromorphic engineering like event-driven processing. Maybe next step would be using new memory technologies, 3D processing, in-memory processing. Yeah, these are some researches that we are already doing at this moment. But for the first, most important things we want to do is that we want to show that it's competitive enough against off-the-shelf products.
One of the ways I know that you're looking at its performance, and seeing how it competes is in terms of power efficiency. And I know that unlike a lot of chips where essentially you can only see how much power it's burning by just looking at the power line that's going into it, that for this, you can look at every single element on the chip. How difficult was that to implement and how well is it working?
First of all, it was very important for us to know the power of each element in the chip. For example, the big controller, the small controller, the processing units. The reason was that we are still in the process of optimization. For example, when in future we introduce this 3D fabrication of Seneca or in-memory processing, we would like to know exactly how much percentage was improved for a given application in different parts of the chip. But regarding the methodology that we have, fortunately, because we are using digital technology, it is very mature. And one of the advantages of digital is that it can be modeled with very high accuracy, very high confidence using computer simulations. So the tools that we are using from companies like Cadence or Synopsys, they allow us to look at toggling of every single transistors, and then they count the number of toggling of every single transistor for a given input data and workload that we provide for the processor. And then basically sum them up, and it allows us to know exactly where the power is going and being consumed, because transistors in the CMOS, in the digital technologies, they are either in a state 1, which consume a specific amount of leak power, or a state 0, which consume an amount of leak power, or when they trigger from the state 0 to state 1 or other way around, that's the part that they consume this dynamic power, because there is a very short moment in time that the transistor is open and allows the current to pass through. By knowing all this timing and the exact model of the transistors, this tool guarantees to tell us that the power consumption of a chip is in this range of, let's say, 10% plus minus 10 or 15%, which is good enough for us to evaluate and benchmark our technologies in detail.
So just to end with, what is your view of the field right now? How close do you think we are to having neuromorphic chips routinely making it into real products?
First of all, it's important to know what neuromorphic means. Neuromorphic chip means, neuromorphic technology means. Different people in my field have different level of standards. Some people believe that silicon cannot be neuromorphic, it should be only brain. Some people believe that digital electronic is not neuromorphic, yes, but my standard is quite low. I think every processor has some inspiration from the brain or has some validation by the brain. I think doing near memory compute or in-memory compute with a lot of small cores, doing a kind of event-driven processing, trying to exploit the sparsity in the data, these are the things that probably make a chip eligible to be called neuromorphic, yes. And if we look at from this regard, there are already neuromorphic chips in the market. For example, the last NVIDIA GPU, which is actually exploiting some kind of a structured sparsity, has a level of bio-inspired compute inside. And there are also a lot of startups, for example, BrainChip. I believe they already have some customers. The Gray Matter Lab, which I was used to work also, I believe they're also very close to commercialize their technologies. But we should know that if we are thinking about a neuromorphic chip like an analog compute platform that does in-memory, maybe using some kind of non-volatile memory technology like memory stores, these are very cool research topics. But there is several levels of technology and application and architecture which need to be matured enough, and they have interdependencies. For example, if a technology is not mature, then the architecture need to consider that into account. So then these dependencies makes it a bit slower for us to have them on the market, but definitely they will be on the market maybe in 10 years.
So to distill that down a little bit, what you're really saying is that there are things that are a little bit neuromorphic by your standard that are routinely out there in the market, and it's just where you draw the line. Some things are less and some things are more. We can let everyone take neuromorphic as being a little bit what they do. So that would be your view of it.
Yeah, the technologies that are developed as neuromorphic, they will be a step by step in the market. It's not like all of them go in one go, but they will be deployed by actually companies that are doing off-the-shelf devices and maybe used to be conventional, but to update their technologies. Step by step, they will be commercialized and go in the market for sure.
Amirreza Yousefzadeh, thank you so much for coming on to Brains and Machines.
Thank you very much, Sani, for this great conversation.
Thanks, Sunny. For more about Amir Yousefzadeh's work, please go to brainsandmachines.net. Now, we welcome back our regular commentator, Professor Ral Etienne-Cummings from Johns Hopkins University.
Hi, guys. How you doing? Good to see you again.
Hi, Ralph. So I need to say straight away that I love the sincerity of Amirreza. I loved it. He's very sincere and honest, and he talked about the PhD with his failures and goals and things that he achieved. Amazing. I also agree a lot with him that we really need to go and to show market value with our platforms and with what we do. And he talks about the car tasks. This has been said by Emre in previous episodes. And I was looking at Akida and BrainChip because we didn't talk enough, I think, about BrainChip. And they also work on car tasks with Mercedes, I think. Then actually, my question is, at the moment, we are not ready and able to show our market value. So I think that what we could do, like for example in Vision, is to fuse and use frame-based and event-based when they are needed, right? So just to go for an hybrid solution for now. What do you think, guys?
Yeah, no. I suppose I'm more in the notion that, look, the frame-based approach is being chased down, is being beaten, is being done, is being processed, is being put into cans and sold on the shelf as much as you want, right? It's there, right? That's the entire computer vision domain. Event-based stuff is the thing of the future. And remember what he said towards the end of his interview is that he wants certain things that are available now. And for that, he went entirely digital, right? Entirely, in my view, simulation-based, right? It's not really building the physics elements, right? And then he said, oh yeah, the pure neuromorphic scenarios, with memristors and things of that sort, that's maybe in 10 years in the future. He said, oh, they're very good research questions right now, but commercially, we won't see it for about 10 years. To me, that's the interesting stuff. The stuff that is being beaten and put on the shelf and so on. It's obviously interesting to see the next Go player or the next system that beats a human at doing X, Y, or Z. Obviously, right? It's interesting. But that doesn't move me. What moves me is when can I get to the point, in his view, the 10-year point, right? So we should be looking at that. And that is vision that basically uses events, uses things that are more biologically, or maybe some other alternative way of thinking about information. I'm not entirely sold to just a biological approach to looking at information processing as being the only thing, right? But something different than what's being done now. So that's why frame is not as interesting to me. And I care more about these other approaches.
I just wanted to add to that one of the problems with frames is frames just intellectually are based on a very pictorial idea of information, which is great if you're Leonardo da Vinci or if you're showing an image to someone on TV, both of which I am very much into, so I'm not dissing. But if you're a machine and your job is not to appreciate an image, but to extract information from it, then actually frames are not a really good way of doing it. I remember back in the 90s, there was a really interesting paper that interestingly got pulled. To this day, I don't know what happened to it. And so for that reason, I'm not going to mention the name of the researcher. But he was basically doing some machine vision research. And one of the things he showed was that actually the most interesting thing going on in the image was where the noise was and where people liked the images the least, right? Because that was in a way where the machine attention needed to be, that they had learned in their lab. And I think there's something to that idea that in making things beautiful for ourselves, which is what frames tend to be about, we're actually fudging and hiding and smoothing away the things that are actually interesting in terms of what is happening in that image.
That is a very interesting point, Sunny, because in fact, I think there was a DARPA project that was specifically about that, the anomalies in the scene. So one could think about saliency as, what is the most likely thing to grab your attention. But then if you subtract out all the beautiful salient objects of the image, what is left? And then how do you attend to those things? And are there interesting anomalies, the crab that's not quite a crab walking on the beach, right? And you might want to go and look at that and say, that is not supposed to be there or whatever, right? So that's a very interesting way of thinking about it. So I didn't know about this paper that you're referring to, but yeah.
I was writing an article a few years ago and I went back to look for it. So somebody had submitted a newsletter piece to a newsletter that I was editing at the time. And I thought it was a great insight. And a few years later, I went back to try and find the paper, and the paper was never published, like a peer-reviewed paper. So it could be that there were serious flaws in it. It could just be they never got around to it. I don't know. But I can't give you a reference to a paper because there never was one.
Oh, it could be a conspiracy theory now. It could be that somebody thought, oh, this is really good. I'm going to keep it for myself.
The newsletter article still exists. It's on my hard drive as long as nobody hacks into it. So there you go. Giulia.
Guys, I don't want to sound picky, but companies and industries just look at us and they tell us, okay, what is working? What we can buy? What do we do with these things? Then I understand that we need to focus our attention on what's interesting, but these are just, let's say, the elite of the researchers that can do that, because 80% of us needs to produce things that actually works. So I understand, and I'm part of this elite because in the papers that I have done, they're not actually commercializable. So I looked at the structure of the network, and I'm fully with you guys. But I honestly agree with Amirreza that we need to compete. And also, I would like to know what you think, guys, about the fact that he's using this double controllers and then he switch off the big one when it's not needed. It feels like hard-coded as a, let's say, solution, but if it works, right? What do you think?
Listening back to that interview, obviously I spoke to Amirreza some time ago, and I thought he was very good at explaining why he did what he did. And I was very pleased with the interview from that point of view because I really felt I got an insight into his decision-making process. And what I liked about it is he does what works and he knows why he's doing it. And that's enough. From his point of view, that's maybe enough. And maybe if we look at what he's doing as a kind of intermediate step, just the same way that deep learning is helping to pave the way for neuromorphic engineering, that people are all of a sudden understanding what machine intelligence can do, and therefore they want more of it, and they want it to be smaller, and they want it to be more power efficient. Maybe likewise, Amirreza will be creating markets for us for the future. And so I don't think I need to be sniffy about that, although I probably would have been 20 years ago. When I was doing my PhD, I would have maybe sniffed at it and said, well, that's not really neuromorphic. But I think there's something valuable there. So I agree with you, Giulia, but I also think that it's an interim measure. I don't think it's the final stop. Not that there ever is a final stop with technology, but I think we're going to find that things are going to change really rapidly. And this is just going to be a continuum, hopefully, slide into a more neuromorphic technology space.
I guess to speak to the notion of the elitism, and I'm an academic elite in that sense, right? In the sense that I don't have to think about the immediate commercializability of things, right? And what Amirreza was talking about was kind of the immediate commercializability. I can think about 10, 15, 20 years, right? And that's what makes things interesting for me. And my perspective is that, look, the moment that Intel and IBM and Grey Matter Labs or whatever got into this space, what it communicated to me was the research on this particular element is mature. I do not need to do the research here. Now it moves into a development phase. And let the startups and so on develop and sell and whatnot. I don't have any compunction to try to stop that. Let that happen. But I still think that the place where we're going to make set the stage for the next phase of companies, the next phase of startups, the next phase of development that's going to happen is what we continue to look beyond the immediate commercializable horizon and let us chase that. So that when those guys come, then they can be commercialized and so on. So that's what I mean by this notion of it's not interesting, but I'm saying interesting in a very loose use of the word, right? It's a question of what can be commercialized now. Yes, the people who do commercialization well should be doing it. Let's still think about the research part.
One other thing I wanted to say about this interview was that in bringing all of these digital techniques to bear in a kind of neuromorphic way, I think he is representing a bit of a generational shift in the sense that there are so many more tools and there are so many techniques that have been developed. Since you were trained as a physicist and electrical engineer, Ral, and I did my training, I think that ability to create a system on a chip, I mean, it used to always be, certainly with optical systems, but I think this was true with neuromorphic systems too, that you would make claims for, oh, this system is so efficient. And then if you looked at it on the board, it was not efficient at all. It was only efficient if you looked at some subset, the little neuromorphic bit that was in the middle. And I think that the kind of techniques he's bringing to bear, which is saying, well, regardless of how we're implementing our neural network, where are we throwing away energy? And maybe if we shoved a controller onto the chip, or maybe if we bring the memory closer so that it's again on the chip and not off the chip, that's saving us energy. So I actually think some of these tricks are things that we are really going to benefit from. However much of a purist you are later on, we are going to need some of these other functions, at least for the foreseeable future. We're not just going to be pure analog neuromorphic or spiking neuromorphic. And having these other functions and starting to think about how do we put these things together. One of the things I remember from reading his papers was, for instance, he's using different kinds of memory to do different kinds of tasks rather than just using one kind of memory. And I think that's a very elegant, mature way of looking at it, is not just saying, oh, well, this is the kind of memory we have that's compatible with our substrate, so we're going to use it. It's just really thinking about each design choice. So I think this will pay off for all of us, even though in some ways it may not be any kind of long-term solution. And of course, he doesn't have to produce anything commercializable in the short term either, right? But I think as a kind of producing toolboxes, he's doing a great job.
I thought that was one of his drivers, though, is that it'll be something that can be immediately applied to the questions that the commercialized side of neuromorphics are looking at, no?
Well, if you think about imec as a company, as he points out, it's a not-for-profit company. So the idea is they would be producing, presumably, intellectual property that they can give to their partners to do interesting things with.
And commercialize.
But I don't think imec itself would be doing the commercializing. I think their partners would be doing the commercializing. And so I think in a way, what you want to do if you're an imec situation is produce some demonstrators that show how pieces can go together to produce the kind of applications you might be interested in, and then those can be spun off for very specific applications. Do you see what I mean? It's more of a toolbox scenario.
Yeah, I get you. I look at the NeuroPixel is a perfect example, right? We started off doing electrodes, recordings, and so on. And then imec had a big group that was working on it, and they developed now this electrode that has thousands, 20,000, 30,000 electrodes on it, right? I can record neurons down at the scale of 10 microns, right? And now this is a commercial. You can buy it. Extremely expensive, for the likes of us, but you can buy it, right? So imec is definitely the developer of IP, but they are also very savvy about licensing the IP to the appropriate startups and developers that will then commercialize, again, for now, not 10 years in the future, but now.
Yeah, and also we need to distinguish between Amirreza as an individual and, of course, his role at imec. So I think I sensed from him a very great intention at some point to go back into directly commercializing things. I mean, he didn't say anything to me, but that's my impression. That's why he went to gray matter, because he wanted to produce stuff that could be commercialized. So I wouldn't be surprised, because he's still, to me, a very young man, so he's got plenty of time to go out and get involved with other startups or bigger concerns and do stuff there. Giulia.
As you were saying before, he finds solutions, right? He found solutions on the things that he was working on. And most of the time, what I feel from us with quotes is that we try sometimes even to transform a bug as a feature, the mismatch, the noise, and these things. What he does is fixing. Like what I can see in front of me is a clever engineer that is fixing problems. And this is what I loved from this interview. Although I still need to understand a little bit better what Seneca does and how it does it. Like I really would like to deep dive into the architecture. Another thing that I understood is that they also have done a master thesis that is like benchmarking and algorithm optimization for Seneca, which actually does comparisons with Brainscale, Nest, and so on and so forth. So which I find very interesting. And he's talking about microwatts, 30 microwatts power. So it seems very interesting what he's doing.
Just to explain a little bit more about the architecture. So as he explained in the interview, what he is doing is not 100% dissimilar to the kind of thing that Andre van Schaik is doing, although he's doing it on a much, much bigger scale and a sort of multi-chip architecture rather than a single chip architecture. But the idea is that it's entirely digital, right? So there's no analog component, and that you're making use of the speed of electronics, the speed of digital electronics, to have lots of different neurons running in sequence on the same little piece of hardware. So as he says, you're using the same neuron over and over and over and time multiplexing it. And so in that sense, when you're talking about mismatch and things, he's not fixing the problem, he's avoiding the problem, right? By going to digital. So that gives you some advantages, but it also gives you some disadvantages. And the disadvantage is this thing to do with memory, because if you're using the same neuron over and over and over and over, each one masquerading as different neurons, well, those disguises have to be stored in the form of memory around the place so that you can swap them in and out. And that's what makes these kind of systems work.
From my point of view, he's just not avoiding it. He's just doing it differently. He just stated that he wants to do it differently, and he's using whatever works and whatever makes sense to be used, right? If we don't start from the base that the only neuromorphic that you can do is analog, then you're not avoiding, you're just doing differently, right?
I don't disagree with you, Giulia. I was just answering the specific point you were making, is that you were talking about mismatch and stuff, and he's not fixing it, he's avoiding it with perfectly good reasoning. I'm not saying his strategy is a poor one. I'm just saying that you can't say that he's fixing a problem when he's not. The mismatch problem is there, and other people are dealing with it in their own ways. And I think the ways that digital engineers would go about fixing a problem will be very different than the ways that people who are looking at variability that they know ultimately they're never going to be able to get around, that they have to just accept that variability is there and have networks that are robust to it.
Or take advantage of it.
Exactly. So I think they're very different approaches. I'm not saying one is better than the other. I'm older now and much more zen and happy for everyone to have their place. But I'm just saying it's not solving that problem. It's getting around it.
And then for me to kind of put in a historical perspective as well, this approach of this time multiplexing system goes back to one of the originators of True North, right? To Andrew Cassidy. His first real paper in this domain was exactly about that, about making millions of neurons on one FPGAs by doing this time multiplexing business. So all of these ideas, they don't sit in isolation. They're standing on giants' shoulders kind of thing, where you take a piece of here, take a piece of there, and build a better and better final result. Same with the toggling between the big and the small controllers, right? That happens in your laptop, in the sense of, if you look at the microprocessor that's in your laptop, there are different clock speeds at which they run. It may use maybe the same machinery, but there is a throttling of the clock speed based on how much processing you need. Similar kind of thing, right? Based on the need that you want, you either go to the big one or the small one, or you can throttle the clocks.
Hey, listeners, as we were putting the final touches to this episode, we contacted Amira again and discovered he'd moved from imec, where he was at the time we'd last spoken, to the University of Twente. We thought we should get you the details of why he moved and his new position. So here's a little bonus interview, just 4 minutes long. So, Amir, I hear you have a new job. Can you tell me about it?
Yes, recently I started a new job in University of Twente as assistant professor. This is because I was 4 years working in imec, and then I wanted to do something a bit different in my career. So one of the goals I had always to be involved in more academic work, to be able to teach to students. I really like to spread the neuromorphic knowledge, for example.
Who will you be working with?
I still need to explore, but I'm part of a group called Computer Architecture Systems. So one of the main goals is to build embedded AI processors. So through this goal, we collaborate with each other. Another point of collaboration, which already happens through writing proposal and also through imec, because I already know people here through imec, was designing new nanomaterial technologies. So basically, instead of using conventional transistors, CMOS transistors, and then many of them to build a neuron. So that group here in Twente is working on nanomaterials, which just one single element, a nanomaterial element, can replicate a neuron.
Okay, and so I understand you're still working with imec. Is that right?
So the idea was that I make myself part-time and I spend part of my time in imec and part of my time in university. The lawyers are negotiating with each other, with imec, to see if such a solution is possible, that I am involved in both institutes. So the project I was working on, it become now more like a super project. So it includes a lot of a smaller project in it. Gets funded by several EU and bilateral collaboration funding. And what I'm doing at this moment involved in that project is through supervising students, like internship students that they do. And I have very good friends in imec, which we always want to work with each other, no matter the bureaucratic situation.
So do you feel that imec is still fully committed to neuromorphic engineering?
Neuromorphic engineering is a controversial topic in any companies that I worked in, because one of the experience I had was that when we wanted to sell our technologies to the customers, which were completely industrial, they didn't want to hear the term neuromorphic because for them, neuromorphic is equal to trouble. So what we did was actually we changed the name of the group from neuromorphic to hardware efficient AI to be able to represent ourselves better to the customer. What happens, in fact, as I said before, is that many of these hardware efficient AI elements, they use neuromorphic principles in them. So what happens in imec is that there is more push for commercialization. These things put pressure on also doing a bit more less risky research in imec, which that was one of the reasons I wanted to make myself part-time with university, because I wanted to be able to have the freedom of doing that research next to the commercialization activity. So one thing I want to say at the end is that when I look back in my career during my PhD, I'm working in two companies and now in university, I have learned a lot of things from my colleagues. Some colleagues, they teach me a lot about neuromorphic because they had neuromorphic background, especially my university supervisor, PhD supervisor. I have learned also many concepts that we thought we invented it in the neuromorphic domain, but that's not true. It was already there a long time back, and I have learned them from other computer architectures, from my colleagues in gray matter lab, from my manager, and also from my colleagues that were in imec. In imec, we had this privilege to work together with a diverse group of people with different backgrounds. So I really appreciate that many ideas we had together was a mixture of the neuromorphic and non-neuromorphic domain, as is discussed. And it just makes things better, not worse.
Oh, wow. Interesting developments. Thanks for this, Sunny, and to Ralph for the interesting discussion. In our next episode, Sunny will be talking to Dr. Elisa Donati, a researcher from the Institute of Neuroinformatics in Zurich, working on bioelectronics. We hope you join us then.
That brings another episode of EE Times Current to a close. Thank you for listening, and thanks to our guest, Dr. Amirreza Yousefzadeh. EE Times Current is available through all the major podcast platforms, but if you reach us at our website, eetimes.com, you'll find a transcript of this episode, along with other resources. EE Times Current is produced by EE Times. It was engineered by me, Taylor Marvin, at Coop Studios in Boulder, Colorado. The segment producer was Stephanie Munoz. Thanks for listening.